Hi there, welcome to this lecture series on matrix algebra. This is lecture 19, part 1, and the topic is on determinants. And this is actually the second lecture we are having on the topic of determinants. In this lecture, we will be looking at determinants mostly using geometric means of understanding some properties of it. Okay, so for example, we'll be using it to compute area, volumes, and we will be using it to test for linear independence. Okay, let's get started. The first kind of an application or property of the determinant is that you can use it to compute the area of a parallelogram. So consider a 2 by 2 matrix A, which looks like this, AB and CD. And then we can take the column vectors. There are two of them, so V1 is the first column, and V2 here is the second column. And then consider the parallelogram Q, which are kind of formed by those two vectors in the following sense. So look at the graph here. So let's say this is the vector V1, and this is the vector V2, and there is an angle between them. And then I will form a parallelogram. So at the end of the vector V2, I draw a vector parallel to V1. And then this one is also parallel to V2, so I form this parallelogram. And I want to find the area of this parallelogram, and let's call it Q. That's the parallelogram is called Q. So from our study of Euclidean geometry, we know that to compute this area, you can take a point on this side and drop it down to perpendicularly and find this value h, kind of a height of it. So the area would be the height times the length of the base. So that will be the norm of V1 times this quantity h. And how to find this h? Well, this h here would be, you can look at this right triangle, and then this will be the length of this side times sine of theta in absolute value. Okay, so this length here will be V2 norm, and then this is sine theta in absolute value. So that is a geometric formula to compute the area of Q. Now we want to show that that area can also be expressed by the determinant of the A matrix. So let's do some derivation. So we recall that the angle theta formed by two vectors can also be computed using the inner product. So it will be V1 dot V2 over the length of V1 times the length of V2. This is a formula we have already derived a while ago. So here the V1 is the first column and V2 is the second column of the A matrix. Okay, now we go back to the area formula, which is V1, length of V1 times the length of V2 times the absolute value of sine theta, and we can express the sine theta as this expression here. So you know that 1 minus cosine square of theta will give you sine square of theta, and then take a square root of it and take the positive value, it will be the absolute value of sine theta. Okay, and once we have that, and then we want to plug in the expression of cosine theta using only the vectors V1 and V2. So this is what we put in. That's the cosine and square. And now we will take this term and move it into the square root and multiply it on both terms. And then the first term here would be this square. So v1 norm square, v2 norm square, minus, and this term times that, the denominator will exactly cancel. I will just have the numerator. So v1 dot v2 norm, inner product square. Okay, so we also know that v1 and v2 takes this expression. So we can plug it in. The v1 and norm square would be a square plus c square here. And then v2 norm square will be b square plus d square, which we put here. And then the inner product of that would be a times b plus c times d, which we put here, and square. And the rest is just algebraic manipulation. We can open this product out into 4 terms, and then open up this square, and then we will see that certain terms will cancel, and in the end we'll have 3 terms left. Okay, and then we'll notice that these 3 terms forms a perfect square, and that's exactly AD minus BC square, okay, and square root of it. And then you can cancel the square root with the square sign, and you get the absolute value of AD minus BC, and which we recognize that is exactly the determinant of the A matrix. Okay, so we can summarize. Consider now we have a matrix A 2 by 2 with 2 column vectors v1 and v2, and we have the following statement. So the absolute value of the determinant of A here is the area of the parallelogram whose sides are v1 and v2. So like this. The absolute value. So here, if v1 is like this, v2 is like this, and you form a parallelogram, and the area of that will be the determinant of that A matrix. Okay, so the second thing is that we realize that there is a sign here, right? Determinant can be both positive and negative, and therefore we put an absolute value sign here. So what causes this sign of the determinant A? Well, that is caused actually by this the angle theta. So which direction is this angle theta defined from v1 to v2? Is it counterclockwise or is it clockwise? Right. So if it is a counterclockwise definition from v1 to v2, then the determinant, the sign of the determinant is positive. Otherwise, if it is clockwise, like in this graph here, and then determinant of A would be negative. Okay, so instead of proving that, let's take an example, some examples of the determinant of it. So let's say we want to compute the area of the parallelogram with sides v1, which is 4, 1, so that's the v1, and then v2 is 1, 2, which is here. Then we can compute the determinant of this matrix, v1 and v2, and we found out that's 4 times 2 minus 1 times 1, which is 7, and it's a positive number. So the area of this parallelogram Q here is 7. Now let's consider 2 other vectors. So one we call W1, which is -2, 3, so it's in this graph pointing that way, and W2 is 4, 1, so which is like that. And then this is the first column, and that's the second column of the matrix here. And so what is the area of the parallelogram formed by those two, this area here? Well, we can compute the determinant of this, and we'll find out it's this is W1, this is W2, so it's -2 times 1 minus 3 times 4, and you work it out, it's -14. So you notice the determinant here is negative, and that is because the angle from W1 going to W2, to form this angle, you are going in the clockwise direction. Okay, And therefore, when you want the area, you have to take the absolute value, so it's 14. We can also use this result to find area of a triangle. Say, let's take this example. Let's say I have 3 points, 3 vertices, A and B and C for my triangle. And the coordinates are given 2, 2 for A, and this B here is 3, 4, and this C here is 5, 1. And I want to find the area of this triangle. So how can we relate this to a parallelogram, the area of it? Well, we see that we can pick any 2 sides and find those vectors, and then we can use them to form a parallelogram. For example, if we call this V1 and we call this V2, then I can form this parallelogram with this blue kind of, all the arrows, this blue line. And we note that the area of this triangle is exactly half of the area of this parallelogram. And then we can use that to quickly compute the area of the triangle. Okay, let's do it. Okay, so let's write out the vector v1 here, which is b minus a. And so it starts from a and points to b. And then you plug in the value of ab and you get 1, 2. And then this vector v2 here will be c minus a. So you take c and minus a and you get 3, negative 1. Okay, and now we form the matrix, let's call it M, using v1, v2 as the 2 column vectors. So it's 1, 2, and 3, negative 1. And therefore, the area of this triangle would be half times the area of the parallelogram, which would be the determinant of the M matrix. So this determinant would be 1 times negative 1 minus 2 times 3. So it's negative 1, negative 6, so it's negative 7, which we can put here. And then the area of the triangle will be half of that, so it's 7 over 2. Okay, so don't you think that's a pretty quick way of calculating area of a triangle with vertices given? I think so. Now let's look at a 3 by 3 matrix and interpret the determinant of the geometrical meaning of that. Okay, so let's say we have a matrix, 3 by 3, and we denote the 3 columns as v1, v2, v3. And then this absolute value of the determinant of A is now exactly the volume of the parallelopiped with the 3 edges v1, v2, and v3. So, for example, here you have a v1 and you have a v2 and you have a v3 pointing in 3 directions with certain length, and you know you can form a parallelopiped. So you can form a parallelogram from this side, and this will be parallel to v3, and you form, and then top is also a parallelogram. So you get that. So for example, here if you have a v1 here, v2's here, and v3 here, you can also form a parallelepiped. So this v1 will be copied here and here and here, and the v3 will be copied here and here and here, and v2 will be copied here and here and here, and you form it. Okay, and the determinant of this matrix A here in absolute value will give you the volume of this parallelepiped. And then, of course, the sign of the determinant of A, it could be positive or negative. So similar to the 2-dimensional case, so the sign here is actually determined by the orientation of the vectors v1, v2, and v3. So here one follows the right-hand rule, kind of. So if you open up your right hand and then stick out your thumb, your index, and your middle finger, they form kind of vertically, they form kind of a coordinate system. Then if you can point the thumb in the direction of V1 and then point the index in the direction of V2, and then if V3 is in the direction of your middle finger, then the determinant would be positive, otherwise it will be negative. Okay, so here you see for this one, you can put your thumb, your right hand side thumb, and then that's your index finger, and this will be the middle finger pointing up. And while here, if you put your thumb this way and you put your index finger this way, then the middle finger is pointing up, but then here it actually points down. So here is not the correct orientation, and the determinant of these three vectors would be negative. Okay, let's take an example. I want to find the volume of the parallelepiped, we call it capital gamma, with the three sides, V1 and V2 and V3. This is in 3D. Okay, so let's draw these vectors in this coordinate system x1, x2, x3, and we find that this is V1, and then V2 will be in the plane formed by x1 and x2 because it has 0 for x3, so that will be the V2. And the V3 is 1, 1, 3, so you have 1 unit in the x1 direction, 1 unit in the x2, and 3 unit in the x3, so it's here. Okay, and we can maybe now check the orientation of the right hand rule. If you have your thumb in this direction and have your pointer index finger there, then the middle finger is pointing in the direction of V3. So we expect the determinant to be positive. Okay, so we use our knowledge about the volume relating to the determinant of A, and we form the A matrix by putting the 3 column vectors in, and then we compute the determinant of A. And you see that this is a upper triangular matrix, so it's just the product of the diagonals. So you get 4 times 3 times 3, which is 36. And then that is the volume of this parallelepiped. Okay. And we see that one can also use this to actually find this height here. So you know that another way of computing the volume here would be compute the area of the base and then compute this height, that is a point, the point here perpendicular vertically drop down to that. So the area of the basis here is in the plane formed by V1 and V2, and the area will be the determinant of the 2 by 2 matrix formed by V1, V2. Okay, so we can calculate that. That will be 4, 0, 2, 3. This 4, 0, 2, 3. Okay, so this 4, 0, this 2, 3, because it's in this plane where an x3 is 0. Okay, so this will be 4 times 3, which is 12. And then we can use that to find the height. And then the height would be the volume divided by the area. And we see 36 divided by 12 is 3. And this is verified because the x3 coordinate of V3 here is exactly 3. So everything is consistent here. Okay, so let's make some connections in the case of R3. So if we have now 3 vectors, V1, V2, and V3, that's in R3. So they are linearly dependent if they lie on the same plane through the origin. So for example, here's the origin, and you have V1, and then you have V2, and they uniquely determine already a plane through the origin. And if V3 is also lying in that plane, that means all three of these vectors lies all in this two-dimensional plane, and therefore they must be linearly dependent. Okay. And then in this case, if they're all linearly dependent, then they all lie in the same plane. That means that height h is actually 0. And then the parallel pipe formed by this will have no volume because they're all in the two-dimensional space. Therefore, the volume must be 0. And since the volume is 0 and the volume is connected to the determinant of that matrix formed by these three vectors, then the determinant must be 0. So this is a result we just had an argument through a three-dimensional case, but actually it's a general property. Okay, so let's take a look at an example for this in 3D. And let's say I have V1 and then V2 and V3. These three vectors are given. And a quick check shows that they are linearly dependent. I can write V3 here as 2 times V1 plus V2. You will see 2 plus 4 is 6, 6 plus 2 is 8, negative 2 plus 5 is 3. And therefore they are linearly dependent. And in this case, we know that the volume of the parallel-piped gamma with those as the three sides should be 0. And then volume equals determinant, absolute value of it, and therefore the determinant must be 0. Okay, and this A matrix would be the matrix of the three column vectors V1, V2, V3. So this matrix must have determinant 0, and the column vectors are linearly dependent. Okay, let's verify that by computing the determinant of this A matrix. Okay, so we can go through these elementary operations, the row operations of A matrix, try to put it into a upper triangular form. So, so first, I can take the first row here, multiply by negative 3, add on top of 2 to make this 0. Okay, so then you will get 0, 0, and you can negative 10, negative 10. That's step 1. And then I want to make this 0, so I can take the row 1 and add on top of row 3. That's this operation, and then that's 0, and I will get 9 here and 9 here, so 0, 9, 9. And then I see that I want to make this term 0, so I can multiply row 2 by 9, and 9 over 10, so this will be 9, and this will be 9, then I can add it on top of the third row. Okay, and then the third row actually now becomes all 0. And let's call this matrix B. And we notice the determinant of B is now 0 because it's upper triangular, but it has a 0 on the diagonal. And therefore, determinant A would be some constant times determinant B, which is 0, so it's just 0. Okay, so now let's kind of turn our attention to something else. That is, all these elementary operations we perform on the row vectors of A, and now we're performing them on column vectors, and we want to interpret them geometrically. Okay, so consider now a matrix A with V1, V2 as its two columns, and it's a 2 by 2 matrix. So let's look at some properties. So we know that if one of the column of the A matrix is multiplied by a constant C, and we know the determinant will be multiplied by C as well. So geometrically, what does it mean? So you have V1 and V2 here, and then you can form a parallel pipe like this, and this area will be determinant of A, assuming the orientation is give you a positive determinant like is drawn here. And then if I take the first vector v1 and multiply by a factor c, let's say c is some value about 1.5, so this v1 now is a bit longer with length 1.5 of v1, so cv1 is longer. And then the matrix here would be the first column, that's the second column, and the determinant will be the area of this parallelogram, right? And then this area will be this area multiplied by c. A second property is that if we to one of the column of A, we add a multiple of another column, then the determinant does not change. This property we know. So if I have v1 here, and then for the v2, I replace it with the v2 plus some constant c times v1, and the determinant of this matrix is the same as the original matrix. So geometrically, what does it mean? So we know the determinant of v1, v2. Let's say here's the graph here, that's v1, that's v2. This determinant will be the area of this parallelogram. And then what would be v1, and we add a c times v1 on top of v2. Well, so this is v2, and let's say c is slightly bigger than 1, so c times v1 is this length here, longer than v1, so we have v2 plus c times v1, and you will end up here, right? And then this is that is your summation, and you want to form the parallelogram now with v1 and then this new vector. So you can continue drawing in the parallel way, and you have this parallelogram. And then you know that this line here and then this line here are parallel lines, and therefore the height of all this is h, is unchanged. So you know the area of this parallelogram is the height times the length of the base. And the area of this parallelogram, the pink one here, is also the height times the base, exactly the same as the previous one. This we learn from geometry. So therefore, nicely, it coincides with the one of the elementary operations we have here, which the step we know that does not change the determinant. So, isn't that neat? Okay, so let's take a break. We stop with this part 1, and we will continue our study in the second part of this lecture. So I hope you enjoyed this one, and I'll see you soon.